Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 25th, 2025, so just about 4 days ago. This paper introduces a generative model for financial data that gets remarkably close to reality. For instance, it generates return distributions with a tail exponent of 3.78, which is much closer to the real-world value of 4.35. The paper is titled, A Diffusion-based Generative Model for Financial Time Series via Geometric Brownian Motion, and as we'll see, the results are really impressive. The authors integrate a core concept from financial theory directly into their diffusion model to better capture market behavior. And looking at the reactions online, it's clear others are noticing the same thing. The community is really highlighting how integrating geometric Brownian motion helps the model better reflect market behaviors. Specifically, things like heavy-tailed returns and volatility clustering, which are notoriously difficult to simulate realistically. This approach seems to be a significant step forward. Alright, and this figure really visualizes that step forward. What we're seeing here is a price time series generated by the model. The key thing to notice is the gray shaded area around the black price line. This represents the model's uncertainty or noise. And you can see, as the price goes up, that shaded band gets wider. This reflects a core idea from finance called heteroskedasticity, which just means that volatility scales with the price, so higher prices mean bigger potential swings. This built-in feature is why the model is so much better at capturing realistic market dynamics. So, how does the model actually achieve this level of realism? Well, this diagram shows the neural network architecture that does the heavy lifting. It's adapted from a framework called conditional score-based diffusion imputation, or CSDI. Its main job is score estimation, which means learning to predict the noise that was added to the financial data. It combines convolutional layers, which spot short-term patterns, with a transformer layer that captures long-range dependencies. Crucially, the model is also fed information about time, position, and the noise level, which helps it understand the full context. Building on that architecture, these plots show exactly what complex behaviors the model is trying to learn from real S&P 500 stock data. These are three classic or stylized facts of financial markets. First, we see the heavy-tailed distribution, which just means extreme price swings happen more often than a standard model would predict. Second is volatility clustering, the idea that high volatility days tend to clump together. And third is the leverage effect, a tendency for volatility to increase after a price drop. These three patterns are the real-world benchmark the model is judged against. So, moving to the results, this grid of plots directly tests how well the models capture that first stylized fact, the heavy-tailed distribution. Each row represents a different modeling approach based on a stochastic differential equation, or SDE, which is just a mathematical way to describe random processes like stock prices. The top two rows show standard models, while the bottom row shows the new geometric Brownian motion approach. What's clear is that the standard models generate returns with lighter tails. They underestimate extreme market swings. But the new model, especially in the middle and right columns, gets much closer to reality. And these superior results hold true for the other stylized facts as well. So, in conclusion, by embedding a classic financial model, geometric Brownian motion, directly into the noising process, the authors have created a diffusion model that generates far more realistic financial data. This new approach better captures the key market behaviors we've discussed, like heavy tails and volatility clustering. This has huge implications for things like risk management and market simulation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.